now it's time to continue. I'm really glad to have Sajid Vermali here.
Thank you for having me here.
Yeah, please.
Thanks. Good afternoon. It's a good feeling and a bit nostalgic feeling to be here. Sometimes I did my PhD 5 years ago in the same research group that Knut is working. It's a good feeling. But today I'm working at Volvo Cars within R&D. I work with software test strategy. I come from a department where we develop the electrification platform for our electric and hybrid cars. So far we have these 4 models where we have a hybrid version of that. So when we mean hybrid, it means that we have 3 additional components compared to conventional cars. We have an electric motor, usually sitting on the back here. We have a high voltage battery, and we have a charging system. Soon, very, very soon, we will have our first pure electric car. Really exciting about that. And actually at this department, we have a lot of people that have studied at Chalmers, and we have a lot of people that actually have studied exactly the same program that you guys are studying. Something that I find usually interesting when I talk to these newly graduated people that work with us, they come from a world, from an academic world, where you have learned to solve differential equations, you have struggled with a lot of states back and forth, you have learned how to do different kind of controllers, PID, LQR, and then you have also learned how to develop some control system based on some models in a higher abstraction level that is easier to develop, and then you also have learned to automatically generate code from these models, super cool. And on top of that, you also now control a quadcopter. That is like super exciting. And you're boosted with a lot of knowledge, with a lot of self-confidence. And but then when you start at Volvo, after 1 week, when I talk to these people, usually this is the feeling that that they experience. You have to be really quiet. I didn't get the speaker. So this is a bit the feeling that people usually get, and what I'm going to talk about the next 40 minutes is a bit to tell you that that what you learn here is exactly what we do at Volvo. Actually, the only thing is that when you scale it up, some complexity comes with that, and that usually leads to some additional steps. And I will talk about these additional steps, and we'll try to explain how we deal with those additional steps, all right? So I will actually start with your project again. I talked to you in a bit, and if I understood it correctly, you got a project description from Knut, right? Then you had a project to try to come up with a controller that could stabilize the quadcopter. So you started with the P controller maybe in the beginning. You generated code out of that, and then you tried on the quadcopter maybe. You maybe didn't get the result that you expected. Then you tried with another controller and an LQR, and then you say, now if I want to tune my parameters and see if everything is working or not, it will be really time consuming to go to the quadcopter back and forth. So let's have a simulation model that we can work with and do this kind of testing much faster. Right, this is more or less, I think, what you guys have done. Now, let's extend the project. So now, I tell you that the quadcopter should pick up a package from a mailbox here at your department, and it should bring it to another mailbox at the HR division, for instance. So you see that, so the first thing we can do is to see if we can break down this feature in smaller features. So you may start to say, okay, so we need to have something that could grab the package, right? And we have to have some method that could read the address and identify the target destination. And you have to somehow fly to the destination using a map or something. And then you have to land and leave the package and then maybe go back to the home position that the quadcopter has and park it there, okay? So, we see, and CNIL tells you that you can do it together. This is too big for a team. So you can all help together and deliver this project, okay? So the first thing you may think is that, okay, let's see if we can split up the job between different teams, and each team will be responsible for one of these items. And then you realize that, navigation and mechanical grabber, that's not maybe the best side, or you may not be expert in these two areas. Maybe the computer science department is better on that, and the mechanical guys are better on construct a grabber. And you ask me, can we get help of them? And he said, yeah, he's friendly enough. And so he says yes. So then we say, okay, then we have two different departments that will try to deliver this project, okay? And each of them will have a delivery. The software teams will have a part of software code, and the mechanical guy will give you a grabber, okay? So we have 4 software parts that are deliveries and 1 hardware part. Let's call the software component, just for the sake of ease, okay? So 3 of them are developed within this class. 1 is developed at the computer science department, okay? So what's next? Let's define how these software components are going to work with each other, to talk to each other. We have to define the interfaces, the signals. You have to have a standardized protocols between these two so that these guys can work more or less independently of you guys. So we have to have some interfaces defined that is really, really crucial, and also define the whole architecture at all. And then you come, okay, now we have, after maybe 2 months, we have done this, and now we want to integrate it with the microcontroller at the quadcopter and see if it's work or not. Do you think it will work? Well, we see some things. We see that the processors seems to be too weak for all of these additional functions. We also see that the battery runs out very fast, and there is some mechanical problem with the grabber. So, we need to modify the hardware. And how can we modify the hardware? Well, we need to talk to the company that actually develops this and say, hey, we have this problem. Can you somehow modify the quadcopter that we can do it in a better way? And then we also give the feedback to our mechanical friends. The grabber doesn't work because of this and that. So the company that we talk to, they say, we don't have any stronger processor that we can give you, but we can add another, say, microcontroller to the board, and you can divide the software component's job between these 2 microcontrollers, okay? Okay, so far so good. Let's call these one of these boxes will take care of image processing and navigation, for instance, and the other one will be the control system. Okay, and let's call each of these boxes an electrical control unit, an ECU, for instance. Okay, so now we have 2 ECUs, and we have another interface here between these two ECUs. Now it's between 2 processors that need to talk to each other as well. So, and the company says, okay, we can give you a more powerful battery as well. Okay. So now we see that suddenly we have different levels of integration. We have one between the software components that you guys develop, and then we have an integration between the software component that you guys develop together with the computer science, or let's call them supplier. They supply something. And then we integrate everything in one ECU, and then we have another integration level integrating the 2 ECUs, and then finally we integrate everything in our quadcopter. Okay? So, let's try it again. Now we have a bit more structure in how we develop our software, right? Still doesn't work? What could be the reason? Now we feel that we have done it in a quite good way. What could be the reason? The reason could be anywhere in all of these levels that we talked about, right? And it's really, really difficult to find a fault when we are at this level. It could be here, it could be here, it could be here, it could be in between the communication between 2 ECUs. So it might be much better to actually test at each level and be more or less sure that when I go to the next integration level, then I'm quite sure that the problem that we will have here will not come up here. We cannot say it for sure, but it's better to test it at least at each integration level. And in order to be able to do that, in many cases we need to have a closed loop system to get some kind of interaction with a component or with a plant model. And since we don't have it here, we start to simulate the components and with different plant models. So we also maybe have a simulation model for the grabber as well. Okay. So this is the way we test. So now the thing is that we have ended up in a quite hierarchical way of thinking, right? We started with a feature, we broke those down to requirements, then we come up with our architecture. At the lowest level, the team started to develop the actual software, then we integrated them in different levels, and that's what we usually call the V model in the industry. This is exactly how we develop software in the car industry. We start with the highest level, we break it down, and then we integrate it step by step and test it step by step. Okay, so nice development strategy, and we're quite sure that we're going to fix this, but then Knut tells you that you only have 6 weeks. So how are we going to deal with this? So let's think of, let's start by spotting the most time-consuming part of this V model. If I ask you, is this more time-consuming or this one? Which one would you select?
The test phase.
The test phase, exactly. And why is that so time-consuming? Because, you know, the more you go up in the hierarchy and the more you integrate more and more stuff, it's quite straightforward that their likeliness to get some faults will increase more and more and more. And you have a lot of interfaces that can go wrong. Maybe you have used one signal lane for some port, another person at the computer science department has used another signal lane for another port. You have supplier communication. You may ask a computer science guy, hey, can you add this to your model? I need to do that. He may answer after 5 or 6 days. That will delay. So each time you find a fault in this chain, you have to fix that and go through the whole chain again the whole way up. So if you find a fault here, if you find that you go up here and you say that okay, something was wrong here, and you find the cause down here actually, then you have to go back the whole integration levels, and meanwhile many things could be happening. So this looping here could take a lot of time, this will be your bottleneck without any doubt. Okay? So let's see how we can deal with this. How can we integrate and test in a more efficient way? Johan has been talking about it a bit. So let's automate as much as possible. Okay? So just for taking, let's take an example. Let's try to automate the integration for these levels. We skip these high levels just for simplification. Okay. So what are the enablers for automating? First of all, with some help from Knut and Johan maybe, you come up with this great idea to share this code in a common area, so that you can synchronize your code with other people much easier, and you can find some inconsistencies in an automatic way, and there are different versioning tools for that, like SVN, GitHub, you may have heard about them. I don't know, do you guys use GitHub in the project or in the course, or so?
You can.
Okay.
Check out some code.
Okay, good. Then you know what they are. So this is the first thing you may do. The next step is that you want to automate the merging step, because when you get the files from different, there's a lot of CN header files, right? And this is basically what's going to be merged. And the code that you develop needs to be merged with some interface files that will define the interfaces, and also with another file that will define the topology and the architecture, how the software components work with each other. And they have to, they are maybe located at different places. So if we can have a script that could collect these files from different places and compile all of them together, then we can also save a lot of time that is otherwise several manual steps. So let's automate this as well. And then it comes to the testing. So you want us to talk about test cases. So at each level, we want to test, as I said, and we may have a test case that says that, okay, if I input this signal to this model, then the expected output should be like that. And I can actually write a script that could check this automatically, so and give a report to the developer. So we want to automate that part to have a bunch of test cases that are placed somewhere where the developers design or maybe automatically generate, and then we apply that to the system, we execute it, and then we get some report back to the developer. So this could also be automated. And on top of that, we want to automate the earlier steps that I talked about. So that means that each time you submit the new code to this shared place, which we also call repository, then we want a chain of different events to trigger automatically. And there is some server-based tools, usually in the industry it's called Jenkins, that is used for that. So as soon as Jenkins sees that, hey, someone has submitted a new code, then it triggers some job. The first thing is to take the files from the repository, put the files together, compile them, create a software for the whole ECU, and then trigger another activity that will test this ECU based on these test cases, and then giving back the result to the developer. So, and in this way, you can, in a relatively instant manner, get some feedback how it went. So you can do your code at this level, but you can actually get the feedback from the ECU level, how your code impacts the software on the ECU level in a quite fast way, and this will actually help you a lot to save time and to increase the quality of the software you're developing. This is called continuous integration in the industry, and this is one of the most hot topic now in the area because the automotive industry has traditionally been a hardware company. The companies that have existed nowadays, we go more and more and add more and more features to the software, to the car, and that leads that we get more and more software involved. So now the car companies are trying to evolve from being a more or less pure hardware company to more a software company, and with that, these kind of paradigms come to the picture. Okay, so you see that just by extending the project description a bit, we get suddenly much more additional steps that we need to deal with compared to the simple way of implementing the software. Okay, and now you may get a bit more feeling what additional steps I'm talking about, but then I also tell you that we have 120 ECUs in a car. And in an XC90 T8, which is a hybrid version. And imagine that all of these ECUs need to integrate with each other and needs to communicate with each other in a quite complicated way. And that, of course, adds to this complexity much, much more. And on top of that, we have different things that we have to think about. Safety and reliability. We have some safety critical systems in the car, steering wheel, braking. We cannot take the risk that the steering wheel suddenly doesn't work or the brake doesn't work. We have to, for those safety critical systems, do much, much more exhausting testing to be really, really almost sure that they always will work. And, or for instance, you cannot rely that the ECU controlling the braking, for instance, only will have one processor. You need to have some redundant processors, maybe, that if this one shuts down, we still have another processor. We also talk about quality assurance. We cannot afford that our customers sit in a car and the radio doesn't work. They won't buy the car next time. We are adding new and new features all the time. We are increasing the dependencies in the car more and more. We have a lot of suppliers that we work with. We are some parts of the technology that is not counted as our core technology. We use our suppliers to do that, and the communication with the suppliers are not so efficient or easy always. And meanwhile, during the project, we actually change a lot of requirements all the time. So the teams needs to be really agile and be able to adapt themselves to the changes that come. And finally, we are in a very exciting era in the automotive history. No one knows really what comes into the future. A lot of things are happening right now. If we compare to the 90s, for instance, where most of the effort was put on tuning the combustion engine, calibrating the combustion engine for 10 years, 20 years. Now we have passed that phase. Now we talk about electrification. How will that impact the infrastructure that we have in our city? When will we have pure automated cars that could pick you up at one place and take you another place? How could that automated car impact the infrastructure? If you have a really precise car that could drive automatically in a much precise way, then you don't need to have so wide streets. You may have some narrow streets. Then you will have some wider sidewalks. You can have more parks. Everything are connected to each other. And also, with the advancements we are having in technology from different sides, we will see a future where the cars will talk to each other. How will that connectivity impact the business model that we're working with? We may not own a car in the future. We may share a car in the future. We are seeing statistically, we are seeing that from the Trafikverket that people getting their driving licenses, the average age is increasing. When I was 18, I took my driving license the day after. Now we're seeing that people wait a bit more. So the interest is also converging. So all of these brings the complexity to the picture, put the complexity into the picture, and we also have a lot of people working. And the more people, usually the more complicated. We are humans after all, and they are not so easy always to get all people together at one page. So if you didn't know about this, then it might not be so strange to react like this. So this was just an introduction of telling you that what you're learning here is exactly what you're doing there, but you also have to be aware about the big picture, and hopefully it will not look like that. So now I'm gonna go to now I have 20 minutes left, okay. So now I'm going to go to the more on the Volvo side and talk about how we work there, and we'll start again by explaining these challenges that I talked about, but in a Volvo concept, not the quadcopter concept this time. And the focus from now on will be testing. Okay. So I will start by giving you a true story. 5 years ago, we had a test engineer in US, and he once called us and said, hey, each time I come to a special curve, I got the anti-spin lights on. I don't know why. I've tried in many different, I've tried to see different reasons. I cannot find the reason. After some months, Volvo decided to send a new car to this engineer, and again the same problem happened, and he was really mad about this. And another guy at Torslanda here in Gothenburg reacted to that and said, hey, I've heard a similar story in Switzerland. Another person had problem with that as well. So that triggered us to go to US and see what the problem is. And we started to test the car in these curves. We drive for hours and hours and hours, tested everything, and we couldn't replicate the fault. So finally we told the engineer, hey, can you sit in the car and drive you this time? And when he was sitting in the car, we see that on this special curve here, he had a higher speed that is not so normal to drive with that speed, and he always was a bit closer to this inner line, and that made the combustion engine to take another speed rotation in the engine, and that led that another gear was used by the car automatically, and the rest just was like a chain leading to one and another one. And then we saw the problem, we drove like that, and we could replicate the fault. So, and that was a bit what Johan was talking about. So no matter how much we have tested, just after a couple of months, people just drive the car in so many different ways. And if we are not lucky enough, we will end up with unsatisfied customers and a lot of money that we have to spend. So, what do we learn from this? First of all, as I have touched it so far, there is a huge number of scenarios that can happen that are not so easy and predict and test. So we have a big complexity here. And also, as you also saw in the quadcopter project, the later a bug is found, the more difficult it is to find the root cause and fix it. Indeed, the cost that we need to put to find a bug, the later we are in the development phase, will grow exponentially actually. So we really want to find the bugs as early as possible. Okay? So now, from now on, this is the V model you saw, but this is more a Volvo picture. So we have the design phase here and the integration and test here. I'm going to talk about these two levels and how we try to come up with efficient test methods for these two integration levels. Okay. Before that, so we are now talking only about one ECU. Okay. And I will talk about where this complexity that I talked about comes from for the electrical cars. Okay, so now we are from having a big scope, now we are narrowing down to one ECU, and the ECU that is, for instance, controlling an electric motor or a charging system. Okay, so I come up with these three items that is usually the main reasons that the software become complex for electrified cars. First of all, the size of the software. So the size of the software, if we start from 98, the downloadable software size in megabytes, you see how it is increasing. So in just in say 20 years, we have had a factor 10 in the increase of the software size, and this, of course, you get a feeling that how complex our system is getting. We also have some mechatronic properties. We have continuous dynamics, and we have fast feedback loops. When an electric motor is rotating, it's the closed loop between the controller and the electric motor is so fast that small jitters or disturbances to the signals and sensors can actually lead that we don't fulfill our requirements anymore. Just an example, say that you have a requirement or a specification that says that the state, say that you have a clutch that connects the electric motor to the wheel axle, okay? And we have a requirement saying that the state of the clutch must be known before applying the torque. Otherwise, we can end up in that the teeth could be broken or some other strange consequences. So we've seen that. If the state, we have seen this actually, this is a real example when we're testing. If the state of this clutch is incorrectly reported, that means that it is open when it's actually closed. It reports open when it's actually closed. And if that just happened for some milliseconds, it's enough that we break the teeth of the clutch, or that the clutch can get stuck in the closed mode, for instance, that we cannot open the clutch. And this could happen only if we do some mistake for some milliseconds. Another one is the integrations level that we have. So, as I said, we have a lot of dependencies, and it's really, really difficult to understand if some component gets do something strange, how that can impact another component in another part of the car. So, for instance, we have seen this example, for instance, that if this is also another example to say how different scenarios we can end up in. So if you go from, if you take the gear and go from reverse to neutral to drive, and do that for a couple of times, and if we wait somewhere there in 50 to 70 milliseconds, suddenly we don't get an electric drive anymore, just with so small time. Or we have also seen that if we inject some fault in a cooling system and apply maximum torque, then we see an increase in the electric motor, and as expected, the torque is limited. That is applied, but suddenly the anti-spin doesn't work anymore, and this is like, in the first glance, there is no connection between these two, and it's really, really difficult to find these kind of faults. So we have this complexity. How can we tackle that? We know that we have a lot of dependencies, and we know that we want to find bugs as early as possible. What is the solution? I've talked about automation. We actually talked about both of them on the quadcopter example, and that is automation and virtualization. Okay, so what do we gain when we have virtual environments? So as you saw, so the software the bugs in the software can be found much earlier. When you have a pure virtual environment, the cost will be much less than having it going to the test vehicle and test it in the vehicle. You can stimulate the system in a much broader way when you are in a virtual environment, like a breach, for instance. You can just start to generate a lot of test cases and stimulate and attack the software again and again and again. And in that way, you will get much higher test coverage. So these are the main advantages of going to a virtual environment, and we are really putting a lot of effort to go into that direction, not only we, all other car companies in the world. The goal is to reach here. If we have on this axle on the most right, if we say that we have a virtual car, right, that's the vision. And at this level, we have a pure automated development phase, more or less. This is just visions. We want to get close as much as possible to this point. So let's see, I want to talk now about our journey when we started here and how we are moving to reach that point. Okay? So we started maybe 10 years ago, I would say, where we were developing the code in C, and there was some person giving the requirements. A developer wrote the code. We had a tester that gave some test cases to the model, tested it, and checked the expected output compared to what the requirement says. And then if it was passed, good. Otherwise, we modify the requirements or the models. So sometimes it is that the requirements actually are not correct. Okay? And so the code was written manually, the test cases were executed manually, the fulfillment was checked manually, and the test cases were derived manually. Very limited simulated tests and no simulation models. Okay, so then we started to do what you guys are doing now. We started to model and to get some kind of feedback loop, and in order to find the bugs earlier in this way. So we get a bit closer to our goal. Then we introduced model-based development. So in this way, we could automatically generate the code. And then we we started to execute. These are the steps that I talk about in the quadcopter project. So we started to execute the test cases automatically rather than that this person should sit and push the button and see what happens. And then we, I don't know how much we need to go into this subject now, but then we started to this is actually related to what Johan said. Then we started to model the requirements from natural language in English to some formal requirements. And we did that in Simulink, which Johan then translated to the STL expressions that you heard about. So in this way, before, when we tested, we had one input signal, and then the tester had an expected output signal, and then he had to come up with this expected output signal each time to see if the requirement is fulfilled or not. In this way, when we have formalized the requirements, then we just give the output to this model, maybe it could be an STL that Johan showed, and then the signal comes out and says true or false, is the requirement fulfilled or not. So you don't need to define the output signal to see if it is fulfilled or not. So we actually automated this fulfillment check also, we are the first car company in the world that have used these formalized requirements in a quite smart way, I would say. So we actually included these models of the requirements in the actual code. So not just in the test environment that we were testing, we also included these models in the actual ECU software. What happens then? The thing that happens is that this is an ECU that I was talking about. So when you have these observer models, you will say, that somehow reads the signal and says yes or no if the requirement is fulfilled. If you can log all of this information and then read it from the ECU, then no matter in which integration level you have used this ECU, even in the car, you can actually see if your requirements are fulfilled or not. And that is independent of who is driving the car. So it could be in the customer car maybe in 5-10 years, I don't know. If we have it in the customer car, each and every one of our customers will be a tester without even knowing that, because we are having some observers that are all the time reading and logging the result if a requirement is not fulfilled, for instance. We can also see among all of these features we have, how often do the customers actually use some of the features. Maybe they don't use them at all, or maybe, very little. And that could also make us to put effort on other parts in our business model. So this is something that we are really, really proud about, and we are not completely there yet, but we are starting to do some initiatives to reach there. And the enabler for this is that we have formalized requirements. That is not so common in the industry, or it had not been at least until 5 years ago. And when we have formalized requirement, that will be kind of the marriage, I would say, between the academic world and the industrial world. And now, we have also, as Johan talked about, we have also started to generate the test cases automatically. And, but we still need a tester that needs to derive the test cases manually as well. Here you have some tools that we use. They are good at different things. So Bridge Johan has talked about, it converts the requirements or the specification to an optimization problem and tries to reach to a point to falsify that requirement. We have QuickCheck that has been developed by Chalmers in the beginning, actually, where they randomly, more or less, generate the test cases. It's not an optimization problem, but it's really, really strong to simplify the very big test cases into smaller test cases, which makes it easier for the user and for the developer to understand what's going on, why this test case doesn't work. And we also have a commercial tool, Test Viewer, And that is also a tool that is used a lot, and the difference is that it's commercial, and it also more or less it's a semi-random algorithm that generates the test cases. So we use all of these three different tools to attack the software when we have submitted the new code. And now we have also starting on the virtual side. We have also started to build the virtual ECU, which we can test in a much more exhausting way. As I said, continuous integration is really important. So how this testing procedure really looks like at Volvo is that we have a repository SVN. Every time a new developer submits a new code, then it goes to a server. At that server, we have some algorithms that attack the software from different angles. Then we have our observer models that will tell us if the requirements were fulfilled or not. And then we store all of these results in an SQL database. And then we can use this SQL database to give the feedback to the tester, to the developer. We can also visualize the results within different dashboards that could be used for project managers. And we can also generate test reports that are needed by many attorneys from legal point of view and many other things. So each night, hundreds of auto-generated test cases and several simulation hours that doesn't cost us so much compared to doing this in the car, for instance. So the software testing journey we have had, it started from the need that we saw that we have to do something about it. We ended up here. We are today more or less here. So we need. It's really difficult to make everything virtual. It's a quite complex problem, but we are striving into that direction, and we're still working on improving the test case generators. That is what Johan's research is about. We want to improve the simulated components, because if you really want to rely on the simulation models, then they have to be really good, because otherwise it could either give us misleading information, or we still may not find so many bugs that we really expected to find with the simulation models. And that actually exactly 43 minutes. That actually ends up my discussion. Thank you.
So we have time for a couple of questions.
One more thing. I really encourage all of you, if you want to be part of this journey, or if you don't want to do a master thesis, contact me and we can talk.
And you need more NPC students.
We need really, I mean, these are actually one of the best students we have at Volvo that come from this program, at our department at least, that I work with. So yeah, be proud where we are.
Good. Yeah. Any questions to start with?
What software do you use for developing software, and then for simulating, and then for checking?
Simulink MATLAB.
Everything in Simulink?
It depends on which department you're working at, but if you go to active safety, when we have collision avoidance mechanisms or city safety things, they have started to use pure C actually, because model-based development is really good, but it's especially good when you have some kind of closed loop behavior and you wanted to implement a control system. At some places, the nature of the code that you develop is not so much control. It may be image processing, for instance, or I don't know, navigation or whatever. Then it's maybe better to attack C from the beginning. But and then for the continuous integration side, when you want to automate as much as possible, it's usually Python a lot, and yeah.
But maybe you can mention that you build physical models in Simscape.
Yeah, of course. So yeah, MathWorks products basically. So yeah, so we build physical models in Simscape, exactly, and some other tools sometimes also. Yes?
You gave an example of Knut giving us a 6-week deadline.
Yeah?
How long is a usual deadline?
So when a project starts, since there are so many different parts that needs to be integrated, we have to have some specific integration points that everyone integrates at the same time. Okay, so we usually have 4 times like that, and so 4 milestones, and between each 2 milestones you have 12 weeks. So 12 weeks time 4. Let's say 1 year, but then you have to consider that now we're talking about software part. Then it has to be integrated with the hardware, and there is many other tests that are not pure software, and that will usually take it to maybe 2 years or something.
Okay.
Yeah. Thanks.
Thank you. And let's see you again on Thursday, and then we'll sort of summarize